We've seen how the sum of areas of narrow rectangular slices of the region under a function curve gives us an estimate of the area of that region. If we increase the number of rectangles toward infinity, their widths approach zero, and the sum of their areas approaches the exact value of the area under the curve. This is illustrated in the animation you see at left. So the question is, can we write the definite integral as an infinite sum to allow an actual computation of the exact area? The answer, of course, is yes, and this video will explore how to write such a sum in sigma notation. We start by considering the limit definition of the definite integral, which is the limit of the Riemann sum. Inside the sigma operator, we have isolated one rectangle at some value of x. Its height is the function value at that x value. Its width is the width of one slice of the region. Multiplying the height times width gives us the area of that rectangle. The sigma operator adds all the rectangles from the first to the nth or last rectangle. We carry out this sum using larger and larger values of n such that the value of n approaches infinity. This sum will thus converge to the exact area. But the sigma notation we just saw does not directly give us an expression we can use to calculate the area. We would like to find an expression that uses the interval endpoint values a and b, the function operation, and the index counter k, counting from 1 up to n. We start by noting that there are n rectangles, each of width delta x. This width is 1/nth of the distance between a and b, which is found as b minus a over n. Now we can find an expression for each x value corresponding to the position of the vertical side or edge of each rectangle. Since these x values are in multiples of delta x, starting at x equals a, we can say that each x value is a plus some number times delta x. So the first edge is at a plus 1 delta x. The second is at a plus 2 delta x's. The third is at a plus 3 delta x's. And the fourth is at a plus 4 delta x's. As n increases, we simply create more of these x values in the same way. The kth rectangle's edge is at a plus k times delta x. Now we can see that the height of each rectangle is simply the function value at each of those x values. For example, the height of the third rectangle is f of a plus 3 times delta x, since a plus 3 times delta x is the x value at its edge. But remember that we have an expression to directly calculate delta x, which is b minus a over n. So rectangle number k has an area of its height, f of a plus k times b minus a over n, times its width, b minus a over n. To get the total area, we will just add all of the rectangle's areas from rectangle number 1 to rectangle n. Here's the original limit of the Riemann sum, and here is its equivalent in a more computation-friendly form. We simply replace x sub k with a plus k times delta x, and we replace delta x with b minus a over n. Let's look at a couple of examples to see how simple this really is. Let's start with the definite integral of 6x squared from 1 to 8. We write the limit expression replacing x with a plus delta x times k, and then further replacing delta x with b minus a over n. Notice how the constant 6 stays put. We only need to change the x's, and we maintain whatever operations that the function f directs. Here is the simplified form of the sum. Another example is the definite integral of the natural log of x from 2 to 11. Again, we switch to the limit of the sum, and again we replace x with a plus delta x times k, and we replace delta x with b minus a over n. Finally, simplifying, we get this expression.